All right, so let's take a look at the heat of formation sheet on page 27. So remember, the heat of formation is the summation, and I believe we decided that this was the sign for it, of the products minus the summation of the reactants. Keep in mind the cool thing about all of this is the fact that all of this stuff is energy that's locked in the bonds. And that's going to be important when we think about Hess's law too. We told you yesterday, if you knew the structure of CH4 here, you would be able to see how each of these CH bonds has a certain amount of energy that adds up to this negative 74.8. Or that the CO has a triple bond, which gives you negative 110.5, and the CO2 has two double bonds, which gives you negative 393.5 for a total. So it's pretty cool to look at that. Now, since the states of matter, it does have a little bit of a difference, but we can count on those bond energies doing certain things. The key thing for this is to recall that if it's in its elemental form, then it's at its ground state and it is zero. It is zero. So let's take a look here. We have 3NO2 plus H2O yields 2HNO3 plus NO. Do we have anything here in its elemental form? In class? Outside of class. Davis is shaking and said, no, that's good enough for me. Yeah, all of these are compounds, so none of them are in their elemental form. So let's take a look here. We're going to take the products and we are going to subtract the reactants. So 2HNO3, HNO3 liquid is negative 173.2 kilojoules. There are 2 moles of that, so I will multiply that by 2. It's a summation, so we're going to add to that the NO, which there is 1 mole. It is gas form, that is 90.4. Then we are going to subtract the quantity of the NO2, which there are 3 of them. NO2 is 33.9. We're going to summation that, so we need to add also the quantity of 1 of these H2Os. The H2O is liquid, so it is negative 285.8. Two times negative 173.2 plus 90.4.
The answer is negative 256.
Negative 256 minus 3 times 33.9 plus negative 285.8.
The answer is negative 184.1.
184.1. Let me see that okay. So negative 256 minus negative 184.1.
It's negative 71.9.
We get negative 71.9 kilojoules. Remember, the reason why we multiply these out is because this is kilojoules per mole. So whenever we do this, this delta H of F is negative 71.9 kilojoules. That means for 3 moles of this, 1 mole of that, 2 moles of that, and 1 mole of that. This number, when it's used now, if we want to know about with the amount of NO2, then we need to have moles of NO2. And then we say every 3 moles of NO2 can produce this much energy. That's what you should have done with your mg last time, is you changed the grams of mg to moles of mg. And then you use that. Oh, okay, nice. What's your name again? Elise. If you were in Elise's group, you may want to redo the math if you guys did it all together yesterday, because she just redid it and she got 15%. Before you were looking at 98%. So if you did the work yesterday, you might look it back over. and use that knowledge. Cool, cool. So you can work the rest of these problems, 27 and 28. That brings you to being able to watch this video and watch about Hess's law. But I'm going to talk about Hess's law right now. So if we take a look, Hess's law, you can watch this tutorial as well, and this will help you out. It's actually linked under today's lesson. But basically, Hess found that enthalpy or change in heat is a state function. That means it depends only on the current state of the system. So that means that, for example, if you're trying to get to point Z, you could sit there and go A, B, C, D, E, F, all the way through the alphabet and get to point Z. Or what if you could shortcut from A to M and then M to Z? Well, it doesn't matter, because in the end, it is a matter of a state function. It only depends on if you have Z in the end. All this energy in the bonds and stuff like that, no matter how it gets maneuvered around and around and around, as long as you can get to from one point to the other point, when you're at the end of it, everything is set up. That's the energy. That's the energy. So the cool thing for this is that the energy for a reaction depends only on the initial and final conditions, not the way you got there. So if you can find a way using even multiple, many steps in a reaction, if you can find a way to get from one part to the other part using many different reactions, the amount of energy change right here between here and here is the same as the little increment changes of all of these different parts. So the enthalpy change associated with the reaction carried out in multiple steps is equal to the sum of just the one step. So what we want to do is we want to figure out magnesium plus oxygen yields magnesium oxide. We want to figure out the delta H of that for the laboratory on Friday. Well, you guys already know that magnesium plus HCl can yield MgCl2, right? Well, we're going to use that pathway that you guys had on Friday, or I'm sorry, yesterday, with another pathway, and we're going to be able to basically get this reaction going. That is our goal. And then we will be able to put these together to find the delta H of that reaction. We can't do this reaction because we can't burn that magnesium in water. What will happen if we try to light magnesium in water and then put it in the water, or light it and then put it in the water? What will happen to the magnesium?
It'll go out.
It'll go out. So we can't do it. So we need these little tiny step reactions. And with these, we can basically determine this one jump. So we need to have CO on the reactant side. And in reality, we need to have 2 CO on the reactant side. Do either of these reactions have 2 CO on the reactant side? No. The top reaction, we'll call that reaction A, and then we'll call this reaction B. The top reaction, A, has 2 CO on the product side. Well, we learned that if the process is endothermic this way, if we reverse it, then it's exothermic. So I can rearrange this equation to be 2CO yields 2C plus O2. But instead of being a delta H of negative 221, that delta H now will be of positive 221. If we take a look here, we have C plus O2 yields CO2. The problem we have is our product does not have CO2, it has 2 CO2. Anybody want to take a guess at what we could do to reaction B to make it look better like our product up there? Anyone? Double it. Who was that? Elise? Good. Elise says double it. If 1 mole of CO2 being produced gives off 393.5 kilojoules, then 2 moles of CO2 being given off gives off 2 times negative 393.5.
It's negative 787.
Gives off negative 787. And here's the thing. What we want to do is we have both of these pathways and we have all the energy involved. We don't know the energy of this direct pathway. If what we've done to these two reactants allows us to, in these two reactions, allows us to get this reaction, we know that we're solid. So can we use each of these two reactions to build this primary reaction that we want? Well, here we have 2C on the reactant side of this reaction, and here we have 2C on the product side of this reaction. So just like whenever we cancel out our spectator ions, we can cancel out these guys as well. Now, we wouldn't really cancel these out in the reaction. All we're worried about is the energy being set up correctly.
Do they have to be on opposite sides?
They have to be on opposite sides of each of the reaction.
Okay.
Can you see anything else that is on opposite sides of the reactions? Anybody?
The O2s?
The O2s. So how many of these O2s can we cancel out? We only have 1 on the top one, and we have 2 on the bottom one. We can only cancel out 1. Well, look what's left. We add these two reactions together. 2CO yields, 2CO plus O2 yields 2CO2, which is a match of our reaction up here. So what we can do now is we can add these two reactions. We can also add their adjusted heats to get us to where we needed to be. Negative 221.0 plus, not negative. 221.0 minus negative 787 kilojoules. Dang it, we don't want to minus it. We just add these two. Sorry, guys. 221 don't say kilojoules. 221 plus negative 787.
The answer is negative 566.
There we go. So we add these reactions just like we add their energy amounts, and that gives us the delta H of this reaction. Negative 556, or 566. Next one says, calculate delta H for the following reaction. Well, we have 2N2 plus 5O2 and 2N2O5. Always mess with the singular stuff. If you see O2 in multiple things, leave it be and hopefully it'll fix itself out in the end. Right? So what do we have here? I see N2 on the reactant side, and I see 2N2 on the reactant side of our equation. So what can we do to the bottom one?
Multiply it by 2.
Multiply it by 2 is correct. Good job. So 2N2 plus 6O2 plus 2H2 yields 4HNO3. Negative 348.2 times 2.
It's negative 696.4.
So there we go for that. Anybody to get the next step? I've got that one all set up. Next one. Well, we probably don't want to mess with this one because this one is H2O, O2s, and that's not helping me very much up here. What about this one? B. What should I do to B? You guys see it? What should I do to B?
Would you flip it?
I can flip it because the 2N2O5 is on the wrong side. I need to get it on the product side. But what's the other problem with it?
Then do we need to double it?
I need to double it and flip it, right? I need to double it and flip it. 4HNO3 yields 2N2O5 plus 2H2O. 76.6 times 2.
The answer is 153.2.
153.2. Why is it positive? Because I flipped it. Why is it times 2? Because I doubled it.
Did we flip it and double it so it would match the one above it?
Yeah, we want it to match this.
Okay.
So now I have this 2N2O5 on the product side. We good on here? Guys? Hey, you good? Yeah, this is the weirdest thing we've done ever, probably. All right. So now I have the 2N2. I have the 2N2O5. What do I need to do on the O2s? Somehow I got to get 5 O2s. What can I do to this guy to get 5 O2s?
Add multiply by 10.
Multiply it by
Does
10.
it say half?
It does say a half.
Okay, so yeah, 10.
Multiply that by 10. You guys are forgetting that this equation right here has 6 O2s. So if I multiply by 10, then at the end I'm going to have 16 O2s. Take a look here too. I have these extra 2 H2s on the reactant side. I can't keep these H2s on the reactant side.
So you gotta flip it.
I got to flip it. Does this 2H2 help you out? Or how about these 2 H2Os? So I got to flip it and what? Anybody in here? I got to flip it and then what? Double it. I got to flip it and double it. Check this out. Flipping it. H2O yields H2 1 plus 1/2 O2. The problem here is my H2s aren't going to cancel out and go away. My H2Os aren't going to cancel out and go away. I'm only going to have 5.5 O2. That's why we got to double it. So that's 1, 2, and 2. 285.8 times 2.
It's 571.6.
What do you see that cancels out first? Lark, you picked something up. Cancel that.
H
Oh, Davis is going to come to the rescue. Go ahead, Davis.
for the H2.
H2, two H2s. What else?
The 4HNO3s.
The 4HNO3s. What else?
The 2H2Os.
Two H2Os. What else?
The 6O2 and the 1O2.
6 and 1 will leave us with how many?
5.
5, which is exactly what we wanted. We got 2N2 plus 5O2 yields 2N2O5. Keep in mind, we canceled out everything in that reaction. But that was a path that added energy and was taken. So that means that even if we go from here directly to here, that energy has to be accounted for. Negative 696.4 plus 153.2 plus 571.6.
That would be 28.4.
28.4 kilojoules. Cool. Let's try one from the packet. Let's try on page 30. Let's do this one right here. We have these two reactions. We want to make them into this. So the first thing that you see is what? Why not just take the first thing? Can you find the KCl?
Take the first one and flip it.
First one and flip it. So we're going to flip the first one. KCl plus H2O yields HCl plus KOH. Is that good enough? Just flipping it.
And double it.
We got to double it too. 203.6 times 2.
It's 407.2.
Double, 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 double. All right. H2SO4. Are we good with H2SO4 on the reactant side?
Yeah.
Yeah. HCl. Well, we doubled this and we flipped it and we have 2 HCl. We're good. K2SO4. Well, look at that. K2SO4 is on the product side of reaction B. What's our spectators then? H2O is not seen within this. Here we have 2 H2O. KOH is not seen as a product. Here we have 2 KOH. So we don't do anything to this negative 342.4. Negative 342.4 plus 407.2.
It's 64.8.
The delta H of this reaction is 64.8 kilojoules. Question. About 6 problems that you can work on there.
Did that say 64.8?
64.8 is what I got. That's what the calculator said. Yep, 64.8. So, oh, I got some chats. I never look at the chat. Is the one he said to print? What page is that? Oh, hopefully you guys figured that out. Okay, thank you. Yep. Sorry about that. Need to look at the chats more often. Real quick. Here are the answers to that. If you look at the next day's homework, here are the answers to the formation and the Hess's laws answers. So you're more than welcome to check those out and work through those. I think that everybody in group period 5-6 got all the way through everything. At least the ones in here did. Hess's laws lab is here. I will print that out for the group that's coming tomorrow so that you have a copy to bring into the lab with you. It's not you guys. It's back to our old original, right? Our old original lab teams. So I will make copies of that for you guys to write on. The rest of you, if you want to print it out or whatever, you might want to do that, or you can always just fill it out online just like before. If you want to get ahead, part A of this laboratory, we've already done. We did that yesterday. So that was the volume of the HCl, the initial temperature there. Write a balanced equation, and just like you did before, determine the heat absorbed by the solution. All you got to do is write the answer that you got from the laboratory for question A or B? A. For question A yesterday. And then here, it says using your results, determine your delta H for reaction. That would be question B from yesterday. And then what we will do on Friday is we will do part B. In part B, we are weighing out magnesium. Wait a second. I'm sorry. Part B is what you guys did yesterday. There we go. They look the same. The mass of magnesium, the volume of HCl. So that is part B. So those would be your calculations here for part B, just as I said. We will be doing part A on Friday. Basically what we're doing is something very similar. We're taking magnesium oxide and we are putting it in HCl again, and we're immediately covering the cup, and then we are seeing the magnesium oxide. We're seeing that magnesium oxide in HCl, how it changes it. What type of reaction would magnesium oxide plus HCl yield? Magnesium
Single
oxide.
dis-
Yep. Plus HCl. As he said, that will be double displacement. And what will we get?
hydrogen oxide and magnesium chloride.
We get magnesium chloride. You know the formula for it? No?
Is it MgCl2?
MgCl2. And what else did you say? Hydrogen oxide?
Yeah.
Yep. What's a better word for hydrogen oxide?
Water.
Water. Who was that?
Ava.
Nice, Ava. Water. Obviously, there needs to be some balancing in here. And yesterday, you guys did what reaction? What did you put magnesium in?
HCl.
Hydrochloric acid, HCl. What type of reaction is that?
Single displacement.
Single displacement. What are we going to get forming?
Magnesium chloride and oxygen.
Nope. Magnesium chloride and
Hydrogen gas.
hydrogen gas. If only there was something that we could make with H2 and H2O. What could we react H2 with to make H2O?
Oxygen.
Oxygen. So here are two of our reactions. The third reaction will be H2 plus H2 plus O2 yields H2O. And that will here are three reactions that we use Hess's law to determine the amount of delta H. You'll have to rearrange these equations that you've done from the laboratory, and then basically add up the energies that you collected. You will have three reactions, and you'll arrange them using Hess's law and add them up to get it right here. In reality, the amount you should get when you add that up should be 1,203 kilojoules. So then you will do again the percent error for that. And then there's some application problems down here that you'll finish. Unfortunately, this will probably be the last lab of the year. So I'm glad that we're getting it in. The only other labs that we would have would deal with light. And I don't think that it works well with using camera. So we won't be able to transfer it over to Zoom. But yeah, this will be the last lab of the year. Normally we look through these special glasses and we look at different lights and stuff like that. I don't think it's going to transfer well over the camera. I will try and I'll see. But other than that, this will be the last laboratory grade of the year. Any questions? All right, then. You've got a few different problems to work on. We'll get to the lab tomorrow. And then, I'm sorry, we'll talk about the lab again tomorrow, safety precautions and stuff like that. And then on Friday, we will do it. If you do have any questions, by all means, stick around. Otherwise, have a great day. We'll see you. Claudia, are you going to be here for the lab group tomorrow? Excellent.
So I had a question about the like homework returning in stuff, or like the redoing stuff. So can we redo both homework assignment and like labs?
Yeah.
And so if we turned in one of the like labs in late and we got the late penalty, if we return it in, will it?
Yep, it has to be taken off. Yep, it will be.
Okay.
Yep.
Thank you.
All you got was a late penalty? Yep. Make sure you resubmit it so I have a record of it. But I'm going to turn off all those late penalties, okay?
Okay.
Yep.
Sounds good.
Okay.
Thank
You're welcome. Any questions in here?